When a reaction is at equilibrium, it has a constant value that we can calculate called the equilibrium constant, or Kc. The way that we're going to figure this out is, given this reaction, AA plus BB reacts to give CC plus DD, the equilibrium constant is equal to the concentration of big C to the power of little c times the concentration of big D to the power of little d divided by the concentration of big A to the power of little a times the concentration of big B to the power of little b. The way that we come up with this equilibrium constant is it's equal to the products, the concentration of the products raised to their coefficients divided by the concentration of the reactants also raised to their coefficients. So big A, big B, big C, and big D are all chemical substances. Little a, b, c, and d are all coefficients in the balanced equation. The concentrations are molar concentrations, meaning moles per decimeter cubed, at equilibrium, and that is key. No matter what the concentrations are, the value of Kc will always remain constant for that particular reaction at a specific temperature. If the temperature changes, the Kc is going to change, but at a certain temperature, it will remain the same. We can only incorporate chemicals whose concentrations can vary. So when we're writing out an equilibrium constant expression, anything that's in a solid or a liquid state is not going to be included. So we have two examples here. The first one is iron plus a thiocyanate reacting to give iron thiocyanate. So our Kc would be our products, which is Fe, SCN, 2 plus, raised to its coefficient, which is just 1, divided by concentration of our reactants. So Fe3 plus, that's also raised to the power of 1 because that's a 1 there, and a 1 for SCN. So it's times SCN minus. We are going to include all of them because they're all aqueous. They're not a solid or a liquid. The second one, if we're going to write out our expression, our Kc is going to be our products, which is Hi, raised to its coefficient, which is 2, divided by our reactants raised to their coefficients. So their coefficients are just 1. It's going to be H2 times I2. We're going to include them all because they're all gases. So just to think about what Kc means, if it is large, the concentration of the products is large compared to the reactants because we have products divided by reactants. If Kc is really, really, really large, so much, much greater than 1, it means that we have almost all products and very little reactants. We would say that the reaction goes almost to completion. If Kc is small, that means the concentrations of the reactants is large compared to the products, because again, we've got products divided by reactants. If Kc is really, really, really small, so much, much less than 1, it means we have almost all reactants, very few products. The reaction hardly proceeds. So just one example to calculate Kc. We've got nitrogen and hydrogen combined to form ammonia. Calculate the value of the equilibrium constant for the reaction if the following concentrations were measured at equilibrium at 500 degrees Celsius. we have equilibrium concentrations. So we need an equilibrium constant expression. Again, it's going to be our product, so NH3 raised to its coefficient, coefficient's 2, so it's squared, divided by N2. Its coefficient is 1, so we're just going to leave it as 1. And then H2 has a coefficient of 3, so that one's going to be cubed. To find Kc then, we're going to plug in equilibrium concentrations. So we got 2.00 times 10 to negative 4 squared divided by N2 is 1.5 times 10 to the negative 5. And H2 is 3.45 times 10 to the negative 1. And that will be cubed. So Kc equals sig dig, so we're going to want 6.5 times 10 to the negative 2. There are no units for Kc. Even though it would have units, we are not going to write units, and generally we do not write units.